Merry Christmas, chemistry! We're here for our holiday edition of Ionic compounds. So get your papers ready, get some notes down while we're doing all this stuff. So we talked about ions before. Now we need to talk about ionic bonding. So how these things join together. So ionic bonding is the combination of positive and negative ions, cations and anions, because opposites attract. And that's what's holding these together, these substances. And they actually have a very strong attraction between these. So all ionic compounds are electrically neutral. So our positive and our negative charges must balance out. And really what we're doing is keeping track of the electrons, because electrons don't just fall off of something. They have to be taken. They need to go somewhere. And like we talked about the octet rule, they're not going to be satisfied until they have that like noble gas configuration. So ionic compounds don't make molecules, they make a crystal lattice. So the structure of it, like this is a model for sodium chloride, and it just keeps growing. You can grow crystals. You might have heard of that before. But we can keep adding on parts onto this, and it would keep getting bigger and bigger. But really what it comes down to when we talk about the formula is like what we're doing with the lab with the magnesium oxide that we created from burning the magnesium, is that we're looking for that simplest whole number ratio. How do they compare? How many of these to how many of those? And in this case, we end up with a simple ratio of for every one sodium, there's another one chloride. So unlike molecules that have little sets, like water is in molecules, we have H2O. But it's not just a ratio of a big giant thing like the crystal lattice. They come in little sets, H2O here and another H2O there, and they can stick together and be like that. So formulas for our ionic compounds, right behind my head there. As we're writing the formulas, we always put the positive first. So we have that example, sodium chloride. That's a great poster child for ionic compounds. You think of when we do this, the sodium, like we talked about the rules for the naming, the cations, you don't change the ending of them. We just say sodium. But the chlorine becomes chloride because it takes an electron and becomes a negative charge. So we change the ending of the anions to IDE. So we always start with positive, then the negative in that order. So here's a diagram for the atomic structure of, or electron, the shell structure really, of the sodium and the chlorine. And sodium is 2 in the first, 8 in the second, and then 1 in the third. So it has 1 valence electron. And chlorine is 2 in the first, 8 in the second, 7 in the third. So it has 1 open spot. 1 more to be like argon and have that noble gas configuration, that octet. Once sodium, and as we look down below, once sodium loses that 1 valence electron, it does have an octet. So it's following the octet rules, taking the easiest way out to get 8 in that outer shell. And so is chlorine. So now they both have 8. They're done. Chlorine's not going to take any more electrons. It's satisfied. If it had any more, it would have to push it to a new level. And that's just like how the alkali metals are. They lose those electrons very easily. So this is done. Sodium's done. But now they have charges and they stick like magnets. Now, as we have the Lewis structure, let me make this here. So if I was to show this in Lewis structure, I would show the symbol, and then all the dots that we have show valence electrons. So then if I have chlorine here, it has 7 valence electrons. So I would show it like this. We go with our sides, and then I would see, okay, well this will get transferred over to here, and chlorine then will have its 8, and sodium we see has that filled shell underneath there, like that. So with the Lewis dot structures, it's another tool to kind of look at these. We'll use these a lot more when we talk about covalent bonding, but it's a way you can think about that. As we think of how we are spreading these dots around, we don't pair them up until they're forced to. We go with our cardinal directions, our north, south, east, west, that idea. And aluminum would look like this, or you could have the other one up top, whichever orientation, as long as they're not paired up early. So we think, well, the most, that's AR, the most number of valence electrons you'll ever see is 8, right? So as we think of argon would be like this. The only time that's an exception of that doubling up would be something like helium. Here we would show these two together because it's not following the octet rule. It's done, right? It's not like calcium that has 2 valence electrons that are going to be pulled away. It has its 2, but it's got that filled shell with that too. So it's a little special being like that. So that's how we can use the valence electrons to show the Lewis dot structure to show valence electrons, which helps you figure out how these things are going to come together. Oops, clear my screen. So let's talk about some more formulas here. Magnesium bromide. So if I have magnesium with 2 valence electrons and bromine with 7, we can see, well, bromine, being a halogen, has 7 valence electrons, needs 1 more. So it can steal this one and pull that off of the magnesium. But now it's done. It's not going to add any more. So what's going to happen to this other valence electron? Remember that we're not just adding 1 magnesium and 1 bromine and putting them together like that. We got billions and billions of bromines and billions of magnesium and putting them together and seeing what happens. So there's going to be another bromine around, and that bromine will take this other valence electron like that. So when we think about the formula for magnesium bromide, we always start with the positive. We have MgBr2. So the number always follows the element that it goes with. So we're talking about 2 bromines to 1 magnesium. Another way of thinking of this is a graphical method. I have magnesium with a positive 2 charge and bromine with a negative 1. I made the magnesium 2 blocks high, 2 unit blocks high, and magnesium or bromine's just 1. So how are we going to get these to match up? Well, we need 2 bromines. So then we can think we have a total of positive 2 here. Here we have negative 1 and negative 1, which adds up to negative 2. So negative 2, positive 2, that cancels each other out, and we end up, with 0 overall charge, which we said all ionic compounds should have a neutral overall charge. So a couple ways you can go about figuring these out. So let's try some more. Potassium nitride. So again, we're starting with the positive, and potassium has 1 valence electron. Nitrogen has 5. We know nitrogen wants to have a charge of negative 3 with that to get that octet. So we see it rips this one off of potassium, but it's not satisfied. So again, there's going to be billions and billions of potassiums around, so it can lose that one, and then another potassium comes along and it'll lose that one. So then nitrogen will have its 8 valence electrons, and potassium will be stripped of those valence and have the octet that's underneath. So the formula this time is K3, because we have 3 potassiums and only 1 nitrogen. So that's how we would write the formula for it. Using the graphical method, we can think of nitrogen being 3 units high and the potassium only being 1. So how are they going to even out? Well, here again we have a total of positive 1, positive 1, positive 1. That adds up. Whoops. Yeah, go backwards. Go back. I want to go back. No, don't do that. Okay. I need to go back. There we go. So, another way we can do this is by seeing the graphical method. Now, when I do this, and there's just the positive, for just a positive one or a negative one, you won't see the 1 there a lot of times. They'll just show you the sign. So the same with the halogens being negative 1 charge. You'll just see a negative. So the 1 is implied when you see that. So here we have a total of positive 3, and then this is negative 3, and that gives us our 0 overall charge. Okay, now let's look at magnesium nitride. So, you know, the valence electrons, or the Lewis dot structure showing the valence electrons is kind of a way to get you started, but it can actually be a little, you know, trickier working with it when you have more complicated ones. So let's skip that, and I'll show you a different way as we think about magnesium with a +2 and nitride with a -3. It's like, well, our charges aren't balanced right now. Well, I could add another magnesium. It's still not balanced. So I got too much positive now. +4 and -3, that's not going to work. So I can add another nitrogen, and now I've got -6. Oh, but if I add another magnesium, I get +6. So +6, -6 equals out. One way when you're thinking about these is kind of like what you do with math and fractions. If you had 1/2 plus 1/3, well, what do you have to do before you add those fractions? You need to get a common denominator. So to get a common denominator between these, you think, well, what can we build 2's and 3's up to equal out? And 6 is the least common multiple of 2 and 3. So that's the easiest number for us to use. Now we get into those transition metals that are a little bit trickier, and we have copper 1. So what does that mean? Well, that means copper has a +1 charge. And then we look at oxygen. Well, what's oxygen's charge? It has 6 valence electrons. It's going to want to pick up 2 more. So we think of balancing out our positives and negatives. Well, we have a total of -2 here. We only have +1 here. So we're going to need another copper to give us that total charge. So again, we can think of this like I have 2 of these +1 charges. That gives me a total of +2 here. I just have 1. You know, you don't really need to do this, but 1 oxygen is -2. That gives me a total of that, which adds up to 0, right? So as we think of balancing out these charges, the formula for copper 1 oxide is going to be Cu2O. Excuse me. But this gets people, because they look at this and they see this and they're like, well, that's copper 2. There's 2 coppers, but we're not talking about the quantity. We never talk about quantity with these with ionic compounds. We're only talking about charge, and the only reason we have that Roman numeral there is because copper has choices. So we're telling which charge it has, not how many coppers there are. We never talk about that with ionic compounds. So we didn't say it was potassium tripotassium nitride, right? You just say potassium nitride because that's the only way it's going to work. So there's no choices with it, so we don't need to say the thing with quantity. But copper has a choice of charge, so we do need to differentiate between the charges. So this is the formula for copper 1 oxide. Now, we know there's another form of copper. We could have copper 2 oxide. So that means copper has lost 2 electrons, so it has a positive 2 charge. Oxygen has a negative 2. Well, positive 2, negative 2, that adds up to 0. That's a perfect match. Copper has 2 to give. Oxygen has 2 that it needs to complete its octet. So the formula for copper 2 oxide is CuO. So we got to, again, not look at quantity. Don't get distracted by those numbers there. You're looking at just saying it. Unless it has transition metal with choices, then we have to use the Roman numeral. But other than that, we just say it. So naming it's super easy. If you have whatever, calcium phosphide, you just say it, calcium phosphide. You don't do anything about those numbers. If all you're having to do is name it, naming's it's super easy. Just make sure you change the -1 to "ide," and you're good. So when we have these transition metal ones, that's where it gets a little bit trickier. So let's try a tricky one. So I want to write the name for this one. So I want to figure out what the name of this is. Well, I know it's iron and I know it's sulfide, but I can't just say iron sulfide because iron has choices. And I know that's wrong. So we need to look at the side that we do know. We don't have any choices with sulfur. We know that it's a -2 charge. So we think of that charge. It has to be a -2. There's no choice with sulfur. And we have 3 of them. Well, 3 sulfides is going to give us a grand total negative of -6. Well, working kind of backwards a little bit here. Well, we know the total negative charge is -6. The total positive charge must be +6. And there's 2 irons. So we know there's 2 of these irons. But we think, well, what could that possibly be? 2 times what gives me a +6? Well, 2 times a +3 will give us that. So that's how we can figure out what charge this is. So now I know what charge it is. I can say iron 3 sulfide. Now, if you're super cool, you'd use a Latin name, and this is the second of the irons. Iron could be a 2 + 2 or a +3. So ferrous, ferric. So I could say ferric sulfide. Right? Going back, I probably should have done this. Whoops. Why aren't you working? So going back to this one, again, we know the formula for copper 1 oxide is Cu2O. Well, instead of saying copper 1, we could have said cuprous oxide. And when we do the next one, again, we know the formula now is CuO plus 2 minus 2. We could have said cupric oxide for that one also. So the trickier part is looking at the formulas and figuring out the charges on them and naming the ionic or the multi-state ionic compounds. But as you're looking at the charges, you can easily figure that out. Okay, so we're going to be getting ready to play Ionic Rummy with this. And so when you play Ionic Rummy, you get cards and they have elements on them. Whoops, that's supposed to be a K. So I could have cards like this. Maybe I have another potassium there. Maybe I have a fluorine here. And then maybe I have an oxygen. Sure. Well, I can put my stuff together. I know potassium's a +1 and fluorine's a -1, so I could go like this and make a compound. Put the potassium card with the fluoride card and lay that down and say that is potassium fluoride. Well, that would give you 2 points because you used 2 cards, right? Well, you could also take the 2 potassium cards and the oxygen card, and now you have potassium oxide, which is using 3 cards, so that's worth 3 points, right? So as we're putting stuff together, we're matching up charges and making ionic compounds, and then you have to name it. So if you put this down and said potassium oxygen, somebody could say it correctly and steal your points. Now that also means when you have a card like iron, it's kind of wild because it could be a +2 or a +3. So you could use it in multiple ways depending on what other cards you got with it. So we'll talk more about the Ionic Rummy game, but this is the idea of combining positives and negatives, and we have to have equal positive and negative charge overall, and we always write them with the simplest whole number ratio to show that. All right, so get cracking on that homework, and we'll get some more going before Christmas. All right.